So there. So let's get started. Welcome everyone. I'm welcome to Introduction to Quantum Computing. I'm Henry Yoon. I teach this class, and yeah. So get started. The first thing is all the information about this course you can find on the course homepage. Okay, so there's a URL. And if you ever lose track of it, just look up my name, and on my homepage, there'll be a link to the class. So all the things like assignments and video lectures will all be there. So you can just go there to keep up to date. Okay, so yeah, so today we're going to, so first I'm going to go through a bird's eye view of what quantum computing is about. We'll go over that, maybe about like half an hour or an hour. Then we'll talk about the administrative aspect of the course. And then if there's time left, then we'll jump into the first meaty topic, which is we're going to talk about the physics of computation. Okay, so what's quantum computing? All right. In a nutshell, it's computation, or more generally, information processing. That's based on the principles of quantum mechanics rather than classical physics. So I'm not expecting you to know what quantum mechanics is, because I don't know too much about quantum mechanics. But basically, it's a description of nature at its most fundamental level. Right? So it was formulated in the beginning of the 20th century to explain the behavior of subatomic particles. So people were wondering, how things like the hydrogen atom worked, and our existing theories of physics at the time didn't really adequately explain it well, and so they had to develop this whole branch of physics called quantum mechanics. And I was saying, quantum mechanics was developed to explain, the nature at its most fundamental level, so at the level of subatomic particles. And when people started thinking about what was going on in nature at this really small level, they found that it was really weird and really counterintuitive. And to this day, a lot of people say, even quantum physicists say that no one really understands quantum mechanics. You just get used to it. But I think one of the things that we'll learn in this class is through the lens of computing and information processing, we can start to get some intuition for how it works. But we'll see. So quantum mechanics and its specializations known as quantum field theory and quantum chromodynamics and other things, they're really weird, but it's been spectacularly successful at explaining microscopic physical phenomena. So like I was trying to explain, things like superconductivity or superfluidity, these are natural phenomena that you can see in the lab. You cool things down to near absolute zero, and you see all these weird things like there's no resistance when you run an electrical current through these magnets, or you put, you cool helium down to near absolute zero, and there's no viscosity. All these weird things you can only properly explain if you take into account quantum mechanics. Okay, so really, to our best understanding, nature really operates according to these weird rules. Okay, so why do we want to base a form of computation off of this weird theory of nature? And really the starting point is that there's this notion of quantum mechanics and quantum physics being exponentially complex. So what do I mean by that? So, it's been nearly a century of study. We've been looking at quantum physics for 100 years now. And to this day, the best classical methods that we have for predicting the behavior of some general quantum system requires exponential resources. Okay, so what do I mean by that? So let's say you have a handful of particles, maybe like some number of electrons or atoms or something like that. The state, to fully describe the state of these n particles, you need 2 to the n numbers to describe. Okay. And for not too large n, 2 to the n is a huge number, right? We're all familiar with exponential growth and exponentially large numbers. This is one of them. And just to give a preview into the math of quantum information, the state of n particles in quantum physics is described by a vector of 2 to the n numbers. It's a complex unit vector. So, for n, that's like 300, 300 particles. That's not a lot, right? This is like the number of particles in a single uranium atom. Just to describe this, if you were to write down its full quantum mechanical description, it would require a piece of paper that's bigger than the size of the universe. Okay, it's just kind of crazy. Like, how does nature keep track of all these numbers, right? How does nature know the description of the single uranium atom? But as best as we can understand, nature is really doing all of this bookkeeping and all of this computation on these exponentially large vectors behind the scenes. And that's kind of the starting point. We want to take advantage of this extravagant amounts of computation that nature seems to be doing in a way that's useful for us. Right? So given this, you might ask, well, if it's so hard to do computations or keep track of quantum information or the quantum state of some physical system, how have physicists been able to do quantum physics for the last 100 years? Right? And there's a bunch of answers to this. So answer number 1 is, well, they've developed 100+ years of extremely clever approximations and shortcuts for doing calculations. If you're a physics majors, you've probably seen, or learned about these concepts like the beta ansatz, Feynman diagrams, perturbation theory, mean field approximations. I mean, this is the bread and butter of what physicists do, and they're just very, very clever ways of shortcutting this exponential complexity and actually getting useful answers. Okay, so that's answer number 1. And it's been very, very successful. We've done a lot of really cool things with quantum mechanics using these approximations. More recently, in the last 50 years or so, with the advent of computers, classical computers, people have developed these really sophisticated computer simulations, right, to simulate quantum physics. And they develop all these computational tools, like density functional theory, quantum Markov chain Monte Carlo, and so on. There are these algorithms that help people simulate quantum physics and try to predict how quantum systems behave. And really, I think that another answer is that so far, quantum physicists have really just studied systems that only allow for answer 1 and answer 2 to be applicable. It's kind of like this this parable of this drunk person who lost his keys at night, and he's looking for his keys. I mean, he dropped it off in somewhere off in the distance, but he's looking under the place where it's lit, right? And clearly the key is not there, but he's just looking there because that's the only place that he can feasibly look, right? And that is, in that spirit, that's sort of what quantum physicists have kind of done. So now they've studied systems that are mostly classical. Okay, they have some quantum effects, but they're not that strong. They look at systems that have interacting particles that only interact weakly with each other in this quantum fashion. And it's kind of lucky that most of the things that we've studied so far fall into this category, which allows for these approximations and these computer simulations. But when we start to look at more complicated systems, more exotic quantum systems, this superconductors or superfluids, we don't have a full picture or a complete understanding of how these systems work, and that's because they have very strong quantum effects that are going on, right? And answer, these approximations, these computer simulations appear to fall short. And if you wanted to simulate a general quantum physical system, right, not one of these special ones that are mostly classical, it still seems like a hard thing. And no one's been able to find a fast or efficient method for doing so. So this was a question that Richard Feynman, this famous bongo playing physicist, asked in 1981. He was thinking about this, like, thinking about quantum physics and saying, it seems pretty hard to do all these calculations. I mean, he won a Nobel Prize for doing some clever calculations in quantum physics, so he knows how hard it is to do this. And he was thinking, if I wanted to simulate a general quantum system, right? Someone hands me a collection of particles and says, predict what will happen to these particles in 10 seconds or 10 minutes. Right? And he's thinking, how hard is it to do this? And the way he formulated this question is, can a probabilistic computer, meaning a computer like the ones that you have in front of you, where you can use randomness and so on, can it simulate quantum mechanics? That's the question he asked. And in 1981, he gave a talk about this, just sort of musing about exploring this question. And the conclusion he came to after a very in-depth exploration is no. As far as he can tell, and as far as we can tell, probabilistic computers, classical computers like the ones we have, are not able to simulate quantum mechanics. And he gave it a very in-depth exploration, like, oh, what if you try this? What if you try this? Oh, but that doesn't work. And at the end of his talk, he had a very sort of a emotional conclusion to it, which I think really captures the spirit of this field of quantum computing. He said, nature isn't classical, damn it. If you want to make a simulation of nature, you better make it quantum mechanical. And even from the beginning, he's one of the first people to come up with this idea of quantum computation. He says, by golly, it's a wonderful problem because it doesn't look so easy. Meaning it doesn't look so easy to build a computer based on quantum mechanical principles. And we see today, 30 years, 40 years later, that it's not such an easy thing, but we're making progress. So Richard Feynman, along with a few other people around in the same time in the early 1980s, they came up with this idea of why don't we try to build computers that operate based on quantum mechanics, quantum physics. You want to try to take advantage of these weird effects, this weird phenomenon that occur. So let's talk about the early days of quantum computing. What was it like? So, like I said, Feynman and some other physicists and computer scientists came up with this idea of quantum computing. Feynman's motivation for doing such a thing, like I mentioned, is sort of the most obvious one. You want to simulate quantum systems, right? And this is sort of almost tautological, right? Of course, you want to use a quantum computer to simulate a quantum system. And if you brought up this idea to a physicist in the 1980s, they'd be like, yeah, sure, okay, why not? And maybe they wouldn't really appreciate the significance of how different a quantum computer is from a classical computer. But if you went up to a computer scientist in the 1980s, this would have seemed like a wild crackpot idea that there's some model of computation that's more powerful than the classical model. This has been a core tenet of computer science up till then. Even a lot of computer scientists today still really dearly hold to it. They believe that anything that you can consider a computation, you can efficiently simulate using your laptop. Right? And we'll get into this. This is called the extended Church-Turing thesis. We'll talk about that in a second. Okay, so it was sort of a backwater idea at the point at this point, but some people started looking at it. So David Deutsch, who's one of these originators of the quantum computing proposal, he found an example of a problem not coming from physics that could be solved faster on a quantum computer than any classical computer. Here, faster is by a constant factor. Like you can solve it twice as fast on a quantum computer than a classical computer. So maybe it's not so impressive, this factor 2, but it's still something. You can rigorously prove that there's something you can do with a quantum computer that no classical computer can do unless you expend twice the amount of resources. And then in 1992, Bernstein, Vazirani, and then Dan Simons found examples of problems where you could get a much more dramatic speed up using a quantum computer. In fact, you can get a speed up that's super polynomial. So, meaning that as the if you don't know what super polynomial means, just substitute exponentially faster here. I think that's a close enough approximation. So there's some problems that you can solve exponentially faster on a quantum computer than with a classical computer. So that's very interesting. But unfortunately, the problems that these examples that they came up with are kind of contrived. They're not the types of problems that you would think of trying to solve or you would consider useful. But theoretically, it's very interesting. But really, the turning point came a couple of years, like a year later, when Peter Shor came up with a quantum algorithm. So he extended this algorithm that Dan Simons came up with to solve a problem that's actually very interesting and very important to a lot of people. And that's integer factorization. What is this problem? So you're given an integer n, positive integer. You want to output its prime factorization. So every integer can be written as a product of prime numbers. Basic fact. You want this a computer or an algorithm to figure out what a prime factorization. So this is a problem that has nothing to do with physics ostensibly, but it turns out that using these strange properties of quantum information in quantum physics, you can solve this problem efficiently. And does anyone know why this is a significant
public key proof?
Exactly. So this is a significant problem to solve because the security of this RSA crypto system, which is the most widely deployed public key encryption scheme today, crucially relies on the fact that there is no efficient algorithm to solve it. Right? When you get this, conduct credit card transactions on the internet, you're relying on the fact that no one out there has the ability to efficiently factor numbers. If they did, they would break the scheme. So when this came out, this was sort of shocking, right? People were absolutely floored. And since then, that's sort of really motivated one of the main motivations for trying to want to build or understand the possibilities of quantum. So since 1993, since Peter Shor came up with this algorithm, physicists and computer scientists have been faced with three options. Number one, quantum mechanics, this theory that's been studied for over 100 years, maybe it's wrong. Maybe it's an incorrect theory of nature. So that's one option. Number two is maybe there's actually a fast classical algorithm for factoring. You don't need a quantum computer. Maybe we don't know of one, right? But maybe there is one out there that someone, that we just haven't figured out yet. Okay, that's always a possibility. Option number three is that quantum computers are actually more powerful than classical computers. And the crazy thing is, at least one of these options must be true. And each one of these would be extremely significant for math, science, physics. So just to, out of curiosity, I'm curious, which of these do you think would be most likely to be true? So does anyone think that option number one is likely to be true? Not taken. Yeah, yeah. I mean, why not? I mean, classical physics was turned out to be an inaccurate theory of nature, right? At some level. So maybe quantum mechanics is, it's a good enough approximation in certain situations, but maybe in other situations it's actually a really bad approximation. No, that's always possible. Does anyone think that there's actually a fast classical algorithm for factoring? Yeah, maybe. Okay, so, okay, what about number 3? Okay, you guys are optimists. So let's talk about these 3 options and sort of think about why, if any one of them were true, it'd just be extremely interesting and significant. So option number 1 is, yeah, maybe quantum mechanics is wrong. But like I said, to date, it's the most successful theory of nature that we've ever come up with, right? It's made predictions about, like the mass of the electrons in like 11 decimal places, which is just absolutely bonkers. Okay, and we've never found an experiment that contradicts quantum mechanics, right? And in science, this is extremely rare. I mean, there's, even with some of the best theories, there's always like a small fraction of experiments that, find some disagreement. Okay. So it'd be kind of amazing if we found that is wrong and we needed a replacement theory. Option number 2, maybe there's a polynomial time needing efficient classical factoring algorithm. But this would also be very surprising because this RSA crypto system has been out for nearly 50 years. Right? It was invented in the 70s. And, like I said, the entire infrastructure of e-commerce and our internet communications relies on the assumption that it's a secure crypto system. So there's an enormous economic and political pressure to discover any weaknesses if it exists. Right? A lot of people speculate, oh, well, maybe the NSA, in their caverns, they have some mathematicians who discovered a fast classical factoring algorithm, and they're using it to read all our secrets and so on. Maybe that's always possible, but it seems unlikely that only they would have access to the mathematics to do this, and no one else could figure this out. So maybe you can say that just due to the test of time and due to all the incentives, it seems unlikely that there is such an algorithm. Okay, so the option number 3, which seems to be the most popular one here, this would be significant because, like I mentioned, it would refute something called the extended Church-Turing thesis. So let me first explain what the Church-Turing thesis is. So it's named after Alan Turing and Alonzo Church, and they both, these are mathematicians from the 1930s, and they were some of the first people to come up and formalize the notion of computation, classical computation. And their thesis was that a Turing machine, so a Turing machine is this mathematical model of computation, it can simulate any computation process. So this is not a theorem, it's not a mathematical statement. It's more of a principle saying anything out there, if you go out there into nature and you see something that you would call a computation, that thing can be simulated by this Turing machine, right? And to put more concretely, meaning that your laptop can simulate this computation process, however it works. So this is the Church-Turing thesis, and it's a very deep principle that says that, if you want to study computation, you just have to understand Turing machines. And there's a follow-up on this, which is called the extended Church-Turing thesis, which says that not only can this process which you see out in nature be simulated by your laptop, it can be simulated efficiently. So, if you see this process that's going on and maybe it solves some problem, maybe it factors numbers, maybe it does something else. If it solves it quickly, then so can your laptop. You can program your laptop in a clever enough way that it can also solve the same problem quickly. That's the extended Church-Turing. And so you can sort of see why this would be in conflict with Shor's algorithm, right? Because here Peter Shor is saying, if you can build this quantum computer, you can use it to factor numbers quickly. So this extended Church-Turing thesis would say, well, so you can use your laptop to do the same thing, right? And this thesis has been something that computer scientists have adhered to for a very, very long time, and they're starting to say maybe it's not true. Yeah, and I said, yeah, option 3 would violate this ECT. Okay, so these are all reasons for why each of these options would be surprising to to people. And the crazy thing is at least one of them must be true, which is very exciting, right? We're going to learn something exciting about either physics or math or computer science by investigating the possibility of quantum computers. Okay, so that was back in 1993. Kind of Peter Shor's album shook the world. Where is quantum computing today? And it's an extremely exciting time on many different fronts. So number one, on the engineering front, we're finally starting to build primitive quantum computers. Right? For a long time, there were these theoretical constructs that seemed difficult to build for reasons I'll get into later. But now we're actually seeing primitive versions of them being constructed. And that's very exciting because we can see, can we actually run some of these algorithms on these machines? To give away the punchline, we're actually very far away from running Shor's algorithm, so you can continue to use Amazon in the meantime. We're making the first baby steps towards it. There's a lot of exciting theoretical developments, right? So Peter Shor came out with his algorithm in 1993, but since then there's been more algorithms that people have come up with. People have come up with very interesting cryptographic protocols that you can use that are secure even if we have quantum computers, right? So the good news is, even if people do build quantum computers, we'll have replacement crypto systems that will keep our information secure, for example. There's a lot of new insights into how quantum computing compares to classical computing, right? Arguments for why quantum computers are actually more powerful than classical ones. And something that I particularly like and I'm very excited about is that there's a reason to study quantum computing, even if we never build a quantum. Not because there are deep connections to other sciences, things like condensed matter physics, or quantum gravity, material science, chemistry, and so on. All of these have been affected or influenced by the study of quantum computing. Thinking about information in quantum terms has allowed people to make advances in, say, mathematics or chemistry, even without having built a quantum computer. So for that alone, I think it's already very valuable to learn and think about this. So let me talk about the emerging quantum computers. So many players, companies, and labs are racing to build scalable quantum computers. You probably recognize some of these logos, probably the first three. These large tech companies are trying to build quantum computers, but there's also a very vibrant startup culture. There are startup companies that are also trying to build quantum computers. And what's kind of crazy to me is that these last three startup companies are now listed on the stock exchange. To me, it's crazy because for a long time, they were just considered scrappy young startups and they're trying to build these machines. But now people take them seriously enough to invest in them. And what's interesting is we're far from the case of having figured out how to build a quantum computer. Right? There's no one architecture that people have agreed upon. So different companies are betting on different horses, right? Some of them are trying to build superconducting qubit-based quantum computers. Others are trying to build quantum computers based on photonic systems, right? So people are trying all these different things out, and hopefully at least one of them will succeed. Hopefully more. But we're at this stage where we're just trying different things and seeing what will work. Up to 2017 or so, quantum computing devices were extremely primitive, right? You were lucky if you could find someone who could build more than 10 qubits, like 10 useful qubits. But suddenly there was this sea change after 2017, and there was a lot of engineering effort, especially because Microsoft, IBM, Google really got into this game, and they put a lot of engineers and scientists on this project. And now we're seeing programmable quantum computers with 50 plus qubits. I think today IBM has a 127 qubit quantum computer. So they're building these machines that are more sophisticated, more advanced. But here's the major problem. These devices are extremely noisy. Okay, and it's for this reason that we're very far away from being able to implement something like Shor's algorithm. And so people say that we're in what's called the NISQ era. Okay, so NISQ stands for noisy intermediate scale quantum. So it's this kind of weird, awkward area of quantum computing, where we have these very interesting devices that we think can solve very interesting problems, but they're extremely noisy and they only have a handful of qubits, 100 qubits. They can't run Shor's algorithm, but you should be able to solve interesting things. Remember that I said if you had a handful of particles, to write down the full quantum description of the particles requires 2 to the n parameters, right? So even trying to simulate a device with 100 qubits is going to require far more resources than we have using our classical computer. Right? So despite being so noisy and so crappy, we can't even properly simulate these things. So there's some hope that you can use these things to solve interesting problems. The major question was what interesting problems can you use these for? Well, Google tried to answer this question. So they reached a milestone in 2019 called quantum supremacy. So they had built a quantum processor, a 53-qubit quantum processor that they called Sycamore. It's this chip right here. It's based off of something called superconducting qubits. What is quantum supremacy? It's supposed to be a convincing real-world demonstration that this quantum computer is solving some problem that cannot be feasibly performed by a classical computer, right? So it's some task that you have some theoretical evidence that if it's solving it, it's doing something that no supercomputer, classical supercomputer can do. And they claimed that they had achieved this milestone. They were able to reach this milestone because they had reached the sweet spot. So 53 qubits is just beyond the reach of Google's compute clusters to simulate in a reasonable amount of time. Essentially, they said this task that we're solving, if we were to try to simulate it classically, it would require 2 to the 53 operations, which is a lot. And Google has a lot of compute power, so for them to say that they couldn't do this, that's a pretty impressive claim, right? So this little chip here is outperforming their entire compute system on this one task. It's not a useful task, but it's some task that you can use just as a demonstration, as a benchmark. So that was incredibly interesting. It generated a lot of press and a lot of news. And what's happened since then? So other research groups have also announced their quantum supremacy results. People who also build their quantum computers, so there's one experiment that was conducted in China where they built a system based on photonic qubits using light particles to encode quantum information. I mean, it's incredibly complicated setup. They also claim that they reached quantum supremacy. But it's kind of a dramatic. There's some drama here because the biggest competitor to quantum computers are very clever classical algorithms. So last fall, I guess a year ago, some group from the Chinese Academy of Sciences, they came up with a very clever classical algorithm that they ran on GPUs to simulate this Google quantum supremacy experiment in 15 hours. So this kind of like was poking the eye of Google and say, hey, this claim you made actually doesn't really hold water. Like if you read the original paper by Google, they said, oh, this task that we're solving, you can't solve in less than 10,000 years on the most powerful supercomputer. Well, they said we just ran this on a bunch of GPUs in 15 hours. So is that bad news for quantum computing? Is that bad news for their experiment? And if you just step away from, sort of zoom out a bit, and it's not really bad news. This was kind of expected, right? So this race between quantum computers and classical computers has just started. And so you expect some jostling to happen, right? The race just started, and so, quantum computers are just getting off the ground, and so maybe quantum computers will be ahead, but then someone comes with a clever classical algorithm, and it just goes back and forth for a little bit. And also this race is complicated. There's no single metric of performance, right? There's different measures of how, what constitutes quantum advantage. But, the expectation is once the dust settles, we expect quantum computers to be light years ahead of classical computers on certain tasks. Right? At some point, this exponential advantage is going to kick in, and then the quantum computer is just going to race ahead and leave everyone in the dust. That's the hope anyways. So let me summarize where we are in terms of the hardware stuff. So we're in this NISQ era. There's kind of a qubit race going on. Like if you read these press releases from these companies, they're like, oh, today we released a 127 qubit computer, and then next year we're going to try to release a 500 qubit quantum computer, so we're awesome. But really, qubit count is not everything. What's really important is you want to scale things up in a way where you don't just have more qubits, but you have better qubits that are less noisy. And this seems like a really tough engineering challenge. But as far as we can tell, there's no fundamental obstacle to building a quantum computer with, say, 10 to the 6 or a million noiseless qubits. Right? And so these different companies like IBM, Google, and so on, they have a roadmap extending out 10, 15, 20 years, where they want to get to a million noiseless qubits, at which point we can really run Shor's factoring algorithm. So it's going to take a while, and there's going to be a lot of technical challenges in the way, a lot of hard engineering problems to solve, but we don't foresee any game stoppers or showstoppers. Yes. Okay. And it looks like these large-scale fault-tolerant quantum computers, they look like they're many years away. How many years? I can't really say. It's really risky to make predictions about these things. There can always be some radical new technology that makes this much more possible much more quickly. But as far as we can tell, it's not going to be like next year or so. So it really kind of, you can think of it as where we are in the quantum computing today is we're kind of in like the vacuum tube era of quantum computing. Right? Back in the early days of classical computing, people had all these primitive ways of building computers based on vacuum tubes. And they were very clunky. They occupied, tired rooms, and they could only do very basic calculations. And it took until someone to invent the transistor before we can really miniaturize everything and unlock the computer age that we have today. And so we're kind of waiting for the quantum equivalent of a transistor to show up. Yeah, and really the biggest open question today in this area is what sorts of interesting problems can we solve on this machine? So let me give a quick overview of what types of quantum algorithms we know about today. So we know that quantum computers give exponential speedups, not for all problems, right? They're not going to generically make all problems solve problems much faster. But for certain problems like structured algebraic problems like factoring, quantum computers are very, very good at. Okay. We can get polynomial speedups for search problems. So what I mean by this is even things like that aren't structured, like you just want to search for an item in a database. Using a quantum computer, you can do this search more efficiently than a classical computer. By polynomial speedup, I mean, let's say you have a database of n items. Okay. With a classical computer, in the worst case, if you wanted to locate a record in this database, you have to search the entire database. So that takes n steps, right? Maybe it's the last one in the database. But with a quantum computer, you can actually find any item that you want in square root n steps on a quantum computer. So this is what I mean by a polynomial speedup. we expect exponential speedups for quantum simulation. So this is going back to Feynman's original motivation. So if you want to simulate quantum physics and chemistry, like let's say you have some molecule that you want to simulate to very high precision. This is something that quantum computers are just going to be able to do just very naturally, right? That's what they're sort of meant to do. And as far as we can tell, this is probably the most important application of quantum computers so far, right? You know, the main reason to build a quantum computer today is not to break RSA, because once we build quantum computers, we'll switch to some other system. But it's really to simulate molecules, design new materials, and so on. So on these near-term quantum computers, people are trying to come up with algorithms that will work on those. And what people have come up with are interesting things like hybrid classical quantum algorithms. So these are algorithms where, you know, we have pretty good classical computers, right? So why don't we use the best of both worlds and sort of have algorithms that take advantage of the strengths of both, right? And so these are these algorithms that, where, you know, the classical computer will do some computation it's good at, feed it to the quantum computer and have it crunch some numbers and have some cycle like this to try to arrive at some answer. So this is a paradigm that people have thought about. There's also algorithms for quantum machine learning. Okay? People want to perform machine learning on quantum computers and try to see, can we get an advantage there? And it looks like we can in certain cases. People have come up with these convex optimization algorithms that perform better on quantum computers. You know, things like quantum neural nets and recommendation systems look like they might have some advantages. The jury's still out. And here, the high-level question that is still fascinating after 40 years of thinking about quantum computers is we still don't have a very clear picture of what types of problems have quantum advantage. Right? There's some examples that we've listed, but we don't have some general theory of identifying which problems we should look for to try to get some speed ups there. Okay, and to go back to this, you know, connections with other sciences, you know, there's also some really interesting connections with quantum gravity. So to give some background on this, one of the biggest open questions in physics today is how do you reconcile quantum mechanics, right? This really successful theory of subatomic world with the theory of general relativity, which is a very successful theory for describing nature at its largest scales, right? It explains things like galaxy formation, the Big Bang, and so on. So you have these two extremes, these two theories. And what's interesting is that these theories are fundamentally incompatible with each other, which is really annoying from, you know, like, why don't we have a unified theory that explains everything all at once? And so this holy grail of physics is to try to reconcile the two. And something that physicists are very excited about is that ideas from quantum information and quantum computing could help bridge this gap. Okay, so that's something that they're thinking about a lot these days. You know, so things like there's this black hole information paradox that are still puzzling people. And there might be resolutions to this paradox by thinking in terms of quantum information. Right, so let me point out that this has nothing to do with quantum computers. There's no computational task here, but thinking in terms of computer science and information theory might actually yield resolutions of these age-old conundrums. So you know, here's the high-level question: what can quantum computing tell us about nature? Okay, so you know, this sort of concludes the bird's eye view of the field. And really what I want to emphasize is that it's really the early beginning days of the field, right? We're in this uncharted territory. There's so many questions that we don't have answers to. And so that's one reason why I find it extremely exciting to learn and study. Okay, so now let's turn to this particular class. If you have a question. So what are you going to get out of this class? Well, you're going to learn the basic principles of quantum information and quantum computation. And you're going to learn about these fundamental algorithms like Shor's algorithm. You're going to learn how that works. This database search thing, it's called Grover's algorithm. You're also going to learn how this works. And hopefully by the end of the class, you're going to get a pretty good idea of what the state of the field is. And that's, I think one major benefit is that there's a lot of hype about quantum computing today, and hopefully you'll have a clear sense of what's hype and what's fact. And you can tell all your friends what's real and it's not true. And also, I want you to get a sense of what the big open questions are. Okay, like I mentioned, there's a lot of open questions, and hopefully you'll come out of this, knowing about them. So who is this class for? It's really for anyone, computer scientists, physicists, mathematicians, chemists. And really, I don't require any background except you should have a very solid background in linear algebra and basic probability. You don't need to know much about probability or linear algebra, but the basics you should know very well. And this class is going to focus on the theory of quantum computation. Okay. What this class is not going to cover is how do you actually build a quantum computer, like build it out of real physical parts. I don't know how to do that. I'm a computer scientist. If you want to learn that, you should go take Sebastian Will's course in the physics department. He'll give you much more information about how to construct a quantum computer. Or if you want to learn about quantum physics, sorry, this class is not going to help you. I don't know any quantum physics, but I know about quantum information. Okay, so that's what we're going to learn about. Okay, and just to really hammer in sort of what sorts of things I expect you to know from linear algebra. So these words like vector subspace, inner products, row and column vectors, linear operators, and so on, all of this should not be foreign to you. If you're uncomfortable with any of this, then maybe you should either brush up on your linear algebra class or maybe take it out this class after you've taken linear algebra. Basic probability theory, things like Bayes rule, conditional distributions. This should be like something like the back of your hand. And so as long as you have a good background in these things, then you should be able to handle this class. What's helpful but not required is if you also had computer science theory exposure, like if you've taken like an algorithms class or a complexity class, that'll help, but not needed. Actually, how many of you have some experience with Python? Oh, great. Okay. So one thing I'm going to try in this course that's a little different from the courses that I've offered in the past is I'm going to introduce some quantum programming elements. Okay, something that I'm very excited about. So now all these companies, like I mentioned, Google, IBM, and so on, they've released these quantum programming software libraries. And I think it's going to be a very helpful and fun way of learning the material. And so it'll just require you to do a little bit of Python. And so if you're familiar with that, that'll be helpful. Okay, so any questions before I continue on?
Can you elaborate more on the noise part in the NISQ? What is the noise really about?
What is the noise? Good. So why are these qubits so noisy? And it comes down to the fact that quantum systems are extremely fragile. Okay. And this is something that we'll learn about very soon. Is that quantum systems are sort of like, there are these exponentially complicated systems. But the moment you look at it, you observe it, it sort of hides all of its complexity. It just sort of collapses, and you don't have access to its complexity. So that sort of makes dealing with quantum information very difficult because you want to like harness all this exponential processing power, but if you sort of look at it at the wrong moment, it just sort of gets destroyed. Okay, so it's a very fragile system, and so the tough part is to build a quantum computer where you sort of shield all of the qubits, all of this information from being looked at the wrong moment. let's talk about the class administrative stuff. So this will be quick. The grading is pretty simple. There's going to be 5 assignments. Okay. The first, they're all problem sets that you work on at home. The first one's total are going to be 70%, and the last one's going to be a little more involved because we get it as closer to like a final project. That's going to be 30%. You are allowed to work on these problem sets in groups, but ultimately all the work has to be individual, right? But you can team up with, one or two other teammates to talk through problems and work them out. But everyone must write their own solution. In terms of class resources, there's 2 TAs in this course, John Bastanchi and Yulong Lee. They will hold office hours. They will, they'll essentially hold office hours and help you work through problems. Like I mentioned at the beginning, all the course information can be found on this, my homepage. You just go to my homepage and click the class link. Right? So you see the syllabus. There's a office hours calendar. There's going to be the problem sets, the schedule, and the video links. All of the discussions will be held on EdStem. There's office hours this week, so you can take a look. In terms of a textbook, so there's no requirement for a textbook, but if you want some additional resource, I highly recommend this one. This is affectionately called Mike and Ike because it's by Michael Nielsen and Isaac Chuang. And it's probably the most popular quantum computing textbook. It's very good. So you can get it on Amazon or however else you get textbooks. You can also find links to other quantum computing courses and lecture notes and so on my homepage. Right? There's a resource section if you need other sources. Okay, so your first task in this course is we're going to use Jupyter notebooks for the assignments. And the Jupyter notebooks are going to be run on something called the IBM Quantum Lab. Okay? So maybe this weekend or something, when we have like 5 minutes, just go to the IBM Quantum Lab and create an account. So this will open up some environment where you can run Jupyter notebooks. Maybe just open some of them up and just look through them and get a sneak preview of what some of the materials are. Make sure you can log in by next week because I will release the first problem set this weekend, which you will run on this IBM Quantum Lab. Okay, so good. So any questions about the classroom administrative stuff?
Yeah, so to be clear, it's IBM Quantum Lab. What we're actually be running stuff on a quantum computer from IBM.
Good question. So their lab, it's just like a Python environment, but it has the ability to submit quantum programs to run on their quantum computers. It's some kind of queue system, so there's no, you don't run it immediately, but maybe you wake up the next day and they'll have the results. Their quantum computers are quite noisy, like I mentioned, so you're probably going to get very inaccurate answers. But it's kind of cool to know that you can run quantum programs. Yeah, so that's definitely gonna happen. I'm also talking with the IBM folks to try to get these credits so we get access to their machines much more easily, right? There's this long queue, but I think they have some way where we can sort of shortcut the queue, which would be nice. Okay. So that's it for the overview and the administrative stuff. In the last 20 minutes or so, let's get started with the basics. So we'll just get this started and then we'll pick it up next week as well. So here's the roadmap of this part. So we're going to talk about something known as Landauer's insight, which is about the reversibility of computation. This is and so far we're just going to talk about classical computing, classical information processing, but in this reversible framework. And this is going to set the stage for, it's going to make it easier to understand quantum information. We're going to talk about principles of reversible computing and also the linear algebra formulation of reversible computing. Okay, so in classical computer science, we often see operations like the following, right? So maybe you'll let's say you write some Python code, write some code, you have some variables, and let's say you have this variable A and you did some computation with it. But then at some point you just reset the variable to 0. Right? You just erase whatever information it had, and then when it continues, it's not know anything about what happened before. Or if in the circuit world, let's say you have an AND gate, right? So there's 2 bits A and B that come into the gate, and then it computes another bit C, which is the AND of these 2. So in these operations, information appears to be erased. Right, that's obvious from here, whatever information this variable A had is just no longer there after this point. And with this AND gate, if you sort of trace through the information in the circuit, whatever information was held in A and B is, you lose the identity of both these bits because you go from 2 bits to 1 bit. So obviously you're losing some information. Right, and this is, I don't know, we're used to this and this is not a problem. But really, you start thinking about it, is it really possible for this information to disappear? Okay. What happened to this information in the variable A when I did this reset operation? And so to really think about it, you sort of imagine, okay, well, what's my computer doing in real life? And so you sort of imagine well, okay, so on my computer, this information that was stored in variable A was represented as a bunch of voltages, like 1s and 0s, right? And then at some point I did this instruction and those 1s and 0s just went away. Okay, but did it actually go away? Where did it go? And so you're here, you're really you're forced to think about the physics of computers, right? How are computers actually operating in the real world? But it's kind of weird when you think about this because, well, if you think about the laws of physics, both classical and quantum, right? Any law of physics that we have today, they're inherently reversible. There is no information loss. Right? So really a core principle of physics is that if you have any isolated physical process running in one direction, it can in principle run in the reverse direction. And that's not something that seems to be applicable here, right? Let's say you get to this point, A equals 0, then whatever information you had before is just gone, right? You can't access it unless you made a copy somewhere, right? So how do you reconcile this? One way to understand this is that if you look at things at a microscopic level, you take any physical process, sort of zoom in on how the particles are interacting, and you're just watching a movie of these of some physical phenomenon. You can't tell whether this movie you're watching is running in the forward direction or in the backwards direction. So here's kind of an illustration. Right? Let's say you take these snapshots of a basketball here at different times. Right? So here it says the basketball starting at time 0, and then it gets falls down. Right? Pretty normal. But how do you know that I didn't take a movie of the basketball being, there was some force that made the basketball jump up, right? You kick the basketball. That's also something that can happen. So just by looking at this movie, you can't tell whether the basketball was falling down or it was being kicked up. Right? And that's sort of a basic illustration of the fact that the laws of physics can go one way or the other, right? To distinguish between these. Okay, you know, physics is reversible. Okay, you can go both ways. Right? Even things like, you know, you take an egg, you break it. In principle, this shattered egg can, you know, coalesce back and form this perfect egg. There's nothing in physics that prevents that from happening. Of course, it's highly unlikely. We don't see this in everyday life. But you know, there's nothing forbidding this particular series of events happening where it reforms. Okay, so someone named Rolf Landauer, who's this physicist, in the 1960s, he was sort of thinking about this, and he had the following observation. He said, well, computation is some physical process, right? You have to implement your computer somehow, but physical processes are fundamentally reversible. So what that must mean is that all computations, in principle, can be performed reversibly. And this led to the study of reversible computing, which would later heavily influence the study of quantum computing. So let's take a look at that. So here is how we're going to model and think about reversible information processing. So let's say you have some physical system S. So it's just a box. And it has this system S, this box can be in D distinguishable states, right? So I'm going to give the states these labels, 0, 1, 2, up to D minus 1. Right? I'm putting it in angle brackets, just as some notation to denote the state of the box. And you know, the information of the system is stored in the state. What I mean by distinguishable is that, you know, if I hand you this box and you sort of look at it and say, yeah, it's in state 0, 1, 2, you can easily identify what the state is. Right, maybe it's 0, maybe it's 5. So just in terms of notation, we'll write angle bracket 0 or bracket 5 to indicate specific states. But sometimes we use a variable like x to say that it's in state x, where x is some number between 0 and D minus 1. Okay. So, you know, you have this box as some system. What sorts of things can happen to this box? Well, it can undergo some transformations, which can change the state. So, you know, maybe there's some transformation R that happens to it, some physical process. R happens, and then it changes from state X to some state Y. And the way we write this is using this notation. So this transformation R is going to act on the state X and change it to be equal to state Y. It's like a function. There's an identity transformation that leaves the state unchanged, right? So you apply the identity to this box, and really nothing happens. So X just goes to X. You can combine transformations, like maybe you perform transformation R, and then you perform another transformation U in sequence. So you get this combined transformation UR, right? So note that if I do transformation R first, just by the way of like writing this notation, R is going to be on the right-hand side, right? So it's, you know, if you can probably see where this is going, like why this is connected to linear algebra. But here we have a state X, that's what the box starts in. You first apply transformation R, and then transformation U. So R gets applied to X, it becomes Y, and then you have U applied to Y. All right, so where does the reversibility come in? Well, it's a condition on what these transformations can be. So they have to be reversible, meaning that if you perform a transformation R, you should be able to undo it. You should be able to go back to the information you had before. So there's a bunch of different ways that you can express this. One is that this R transformation is some bijection between the set of states. Right? It's a one-to-one map. Equivalently, it's some permutation on these labels, on these state labels. So it's really just permuting these states between themselves. Another way of saying it is that there has to be this inverse. I guess that's what it meant by the undo feature. where if you run this transformation R and then its inverse, you get the identity transformation, or vice versa, you run the inverse first and then R. So just some very basic examples. Here is a bad example of a reversible transformation. This is not reversible, where you have a map that takes the 0 state to 0 and a 1 state to 0. This would be erasing information, right? So it's not reversible. So that's not allowed. But you can also have things like, here are good examples. You can have the shift transformation. So this is going to take the state A, so A is some variable, and then you just shift it forward. So if this A was 0, then it becomes 1. If it was 1, then it becomes 2. If it was D minus 1, then it wraps around to 0. So this is, you can obviously reverse it because you can just shift it the other way. Identity is also obviously reversible. Okay, so those are the transformations that are allowed. Let's talk about composite systems. So what if you have multiple of these boxes, right? So let's say you have a box S1, it's in state X1, box S2 is in state X2, and you want to have some way of describing the state of these boxes together, right? You want to treat this as one big system. So I'm going to call this composite system S1 tensor. That's what this symbol means, tensor S2. And this is a system now with D times D distinguishable states. And the states are just going to be all possible pairs of states for the individual boxes. Very natural. And so the way we denote the state of this combined system is we use this tensor product notation. So we have the state X1 of the first box tensor the state X2 of the second box. So, this is just notation, but hopefully it should feel pretty natural. And we're going to be doing this composite, putting boxes together, putting systems together, and really to reduce the amount of clutter and notation, we're going to use abbreviations. So instead of writing X1 tensor X2, we often just drop the tensor symbol. Sometimes we even combine the X1 and X2 inside the same angle brackets. Okay, sometimes we even drop the comma, right, depending on how much space we want to save. So when you see all these all mean the same thing, right? This is really referring to a system with two parts. First part being in state X1, second part in X2. Okay. So now if you have this composite system, well, what are the transformations that can act on both of the boxes at the same time? Okay, so there's an obvious thing, which is, what if we have separate transformations on the boxes individually? We have R1 and R2. They don't interact with each other. R1 is going to happen to the first box. R2 is going to happen to the second one. The combined transformation as a whole on both systems is the tensor product of these two transformations. So far, this is just notation, right? So if you had this initial state where Z is equal to X1 tensor X2, what happens when you apply these transformations separately? We have a Z prime that's equal to this combined R1 tensor R2 applied to these two boxes. And the thing about this tensor notation is you just match up things on, so if you think about things on either side of the tensor symbol as being slots, you just match up the slots with the right slots. So R1 goes with X1, R2 goes with X2. Right? You never cross things between the tensor symbols. Okay, and let's say one of these transformations is you don't actually do anything, so the corresponding transformation would be R1 tensor identity. Okay, so is that all the possible transformations that can happen to this composite system? The answer is no. And there could be more interesting transformations that aren't just individual transformations on the boxes separately. So what this means is not all transformations can be written as R1 tensor R2. There are some transformations that actually interact these two boxes together, right? How the state of these two boxes evolves depends on both of these individual states at the same time. So here's an example. So let's say that D is equal to 2. So we're really just talking about bits, right? So there's just two states, 0 and 1. And here is a operation that can act on these 2 bits. It's called the controlled NOT operation. And we call it C0. And how does this operation act? Well, it's going to map 0, 0 to 0, 0, so we've got the same. 0, 1 also to 0, 1. But if, but here we have something different. If the first bit is 0, the second bit's 0, then the second bit gets flipped. Right? So if we have 1, 1, the second bit gets flipped to back to 0. Right? So we call this a controlled NOT because based on the first bit, it tells you whether to apply a NOT gate on the second bit. Right? So the first bit is called the control, and the second bit is called the target. This is a reversible transformation, right? And you can sort of check this for yourself. If you, you end up in this state, you can reverse the operation. Actually, you just apply the same operation. You can go get back to where you were. So you don't lose any information at all. And you can see these two boxes are interacting with each other through this transformation. Okay, so I think we're basically out of time. But essentially, we have all the pieces that we need to talk about reversible computation. Right? So let's say we have lots of boxes or lots of bits together. And we can run a bunch of transformations. Apply a transformation here, then a transformation here, right? And based on the sequence of transformation, you can implement any computation, any classical computation that you like. So we'll pick up from here next time.